everyone. Today, I'll be presenting our research study named Preliminary Investigation of Shoreline Response in San Juan La Union, Philippines. I say Josef B. Antonio, and my members include Josef Burhan, Jose Jerard Lim, Djuric Morales, and Dr. Mario Daler. For the problem statement of our study, coastal erosion has always been part of the coastline because of environmental factors such as winds, waves, and tides, and it has also been supplemented by human activities. As such, the coastline of San Juan La Union has been affected short-term and long-term effects. Additionally, with the study of Bayani et al. In the year 2009, it was found that there has been a prevalent coastal erosion in San Fernando La Union stretch. This might also be happening in the coastline of San Juan La Union. In the main and specific objectives of the study, for our main objective, we investigated the extent of the coastal erosion problem of the coastline and also predicted the long-term erosion pattern. As such, our first primary step is we evaluated the characteristics of the factors of coastal erosion, which includes winds, waves, and tides. Second, we also determined the area which could experience deposition or erosion. And lastly, we assess any changes in the shoreline position and also predicted future shoreline changes scenarios in the stretch of the San Juan La Union coastline. With this, with our methodology, we check on the environmental factors which could affect the coastal erosion. And the one coastal environmental factor is wind data. As such, we got the average wind speed per month in Lawag Station for Pag-asa during the years 2000 to 2019, as indicated on the picture on the right, with a wind speed nearing 3 meters per second, with the most number of times. The blue line indicated the maximum wind speed in kilometers per hour, while the green line showed the average wind speed in kilometers per hour, which is shown on the table on the figure below. As for the wind data, we show the wave height distribution from the years 2000, 2005, 2010, 2015, and 2019, also obtained from the data of Pag-asa. The figures of the data are shown on the right. The values of the wind height are obtained using the wind height hindcasting method. As for the tide data was obtained in the Corimao Tide Station in Ilocos Norte from 2010 to 2020, and we obtained that data from NAMRIA. And as you can see, the figure on the right shows the obtained data from Corimao Tide Station. It also shows the different tide elevation with respect to the mean low water. And using the tide data, we took the minimum, maximum, and average tide elevations from the data obtained from NAMRIA. As for the sediment transport, we made 4 transects. As you can see on the figure on the right, you can see the yellow transect, the gray transect, the orange transect, and the blue transect. Using the wind height casting method for a significant wave height and maximum period of wave. And we also use prevailing wind direction, which is northwards. And for the sediment transport formula, we use 2 formulas primarily, Kamphuis Formula and CERC Formula. For the sediment transport formulas, first, the Kamphuis Formula. So 5 parameters were used in that formula or in that method, which includes significant wave height, peak wave period, slope of beach, mean grain size, and break wave angle. The longshore sediment transport rate per month was calculated in the years 2000, 2005, 2010, 2015, and 2019 for both normal and extreme conditions. For the normal condition means normal weather, while extreme conditions could indicate a storm or a typhoon in that area, which could elevate the environmental factor. As for the normal and extreme conditions, Transect 1 had the lowest sediment transport rate, while Transect 4 had the highest. As for extreme conditions, the wind speed is significantly higher, thus greater amount of sediment transport. The extreme conditions, like what I said earlier, could be indicated by typhoons or storm and such, the higher wind speed. As for the relationship, it shows that higher slope, higher sediment transport, and lastly, higher wind speed, higher wave height, and larger sediment transport. And you can see the result of our data, or at least a snippet, the result of our data in the figure on the right for the years 2000 and 2019. As for the second formula, we use the CERC formula, and it includes two parameters: significant wave height and break wave angle. Similar to the Kamphuis formula, we computed for the sediment transport rate per month in the years 2000, 2005, 2010, 2015, and 2019 for both normal and extreme conditions. For normal and extreme conditions, similarly, Transect 1, we also computed for normal and extreme conditions. For Transect 1 and Transect 4 had the same amount of sediment transport rate due to same values of parameters. Similarly to Kamphuis formula, extreme conditions have greater sediment transport due to the difference in wind speed. And lastly, wave height has increased and sediment rate increases. As for the comparison between Kamphuis and CERC formula, it could be seen that there has been huge difference between the two formulas, especially for normal and extreme conditions. And the percent difference is around 239 to 261%, as could seen in this figure on the right. For the years 2000, 261%, until 2019, 239%. As for the CERC formula, it generates more sediment transport through the empirical coefficient K. Both follow the same trend, which is uptrend, as you can see on the figure on the right. And the trend line used was acquired to predict future shoreline sediment transport. And the regression curve, which was used in our data, was polynomial. Next, as you can see, this is the shoreline profile. We use different maps to obtain this shoreline profile. As you can see, different colors from the year 1985, 2005, 2010, 2015, and 2015. So as you can see, the map of, or at least the coastline of San Juan La Union has moved from per different intervals of years. So next, for the shoreline positioning in the year 1985 until 2020, overall, the main shoreline shoreline movement has been predominantly deposition, numerating around 898.93 square meters per year. And as you can see on the figure, in this area of San Juan La Union coastline, it has been mostly shoreline characteristic of deposition. And while some areas exhibit deposition, some shoreline also exhibit erosion. So from stretch of here, shows erosion, stretch of here, erosion, but then some areas exhibit deposition. So for the change in areas for the different time periods, from the year 1985 to 2005, it was seen to have an overall effect of erosion and net loss of area in a change of area with a negative roughly 5,000 square meters per year. 2005 until the latest data, 2020, as you can see in the three intervals, you can see a deposition characteristic. So in here, a change of area, increase of 10,000 square meters per year. In here, 16,000 square meters per year. In here, 2,000 square meters per year. And a total of change of area, 23,000 square meters per year, or like what mentioned earlier, shoreline characteristic of deposition throughout the time period. As for the characteristics of erosion and deposition hotspots, Zone 10 had the highest change in area in 1985 to 2005, with the deposition in this area, and zone 13 resulted in the highest change of area in 2005 and 2010, with deposition. However, in this figure, it just showed that there has been an erosion. In zone 7 had the highest change of area in 2010 to 2005, which also had deposition. And zone 11 had the highest change of area in 2015 to 2010, which resulted in erosion. As for the shoreline prediction, in the time period of 1985 to 2005, so for the rate of displacement due to deposition, there has been 55 centimeters per year. As for the rate of displacement due to erosion, 143.12 centimeters per year. As such, overall erosion during that time span. And the other data are also shown in the table. As for our future shoreline prediction, first we use linear rate of displacement. We use linear analysis. As you can see, linear increase of data from a time frame of until 40, 50 years onwards, until the year 2050. Scenario 2, as opposite from the linear analysis of scenario 1. Scenario 2, we use a rate of displacement for best fit line to predict shoreline shape in 2030, 2040, and 2050. As seen in the shoreline change in the year 1985 to 2005, as you can see, shoreline scenario 1 is closer, having a deposition of rate of displacement of 131.56 centimeters per year and erosion with 173.04 centimeters per year. Lastly, we check the relationship of the environmental factors, which includes winds, waves, and tides, in the shoreline change. For the 2010 to 2015 shoreline change, for the wind, dominant direction was northwards. As for the wave, there was increasing trend, however, not enough to cause dominant erosion, as the wave height was around 0.1 to 0.2 meters, and then less energy stored in waves. As for the tide, the average tide height was around 128 to 148 centimeters per year, which were obtained for the months of July to September. The effects of tide to shoreline can increase the speed of erosion. And as you can see, the wind plays an important role as it affects all other factors. As for conclusion, we answered our specific objectives. So we saw the relationship between hydrodynamic parameters. We were able to prove it and saw the importance of those roles in shoreline change. Second, the shoreline changes were obtained, and we saw which area was dominant deposition and erosion. And overall, we saw that dominant coastal movement was deposition throughout the years. Lastly, we, the researchers, were able to predict the future shoreline change through linear regression, and having data of, in terms of deposition, was around 131.56 centimeters per year, and in terms of erosion, was around 173.04 centimeters per year. Lastly, for our recommendation to further improve the data collection and analysis of the study, it is need for a controlled experimental setup for the CERC formula. Second, the use of physical modeling to see which areas experience erosion deposition. Third, the use of other numerical tools such as software such as Genesis, Delft 3D, and My21. Fourth, the use of cross-shore sediment transport, as we primarily use longshore sediment transport formulas such as Kamphuis and CERC Formula. Fifth, the inclusion of typhoon and current data. And sixth, conduct actual field experimentation, primarily beach profile survey and beach sediment transport sampling. And lastly, interview with any member of the coastal community member or any government official. Thank you. Thank you so much.